Hey everybody, so remember earlier in the year when we did some polynomial multiplication problems, we would multiply polynomials like m plus 5 times m minus 5, g squared plus 7, g squared minus 7, 3x plus 4 times 3x minus 4, or p minus the square root of 8, p plus the square root of 8. And whenever we multiplied two polynomials of this form, we always ended up with the same type of product. Maybe you remember, but even so, let's take a moment because it's going to be really helpful for refreshing our memory and for this specific lesson to multiply these four out and see what kind of products we get. So for instance, in this first one, if we were to multiply m plus 5 times m minus 5, I think we get m squared minus 5m plus 5m minus 25. And when we combine like terms, this negative 5m and this positive 5m, they'll add to 0. We end up with just m squared minus 25. Now, this lesson is going to be all about how do you take a polynomial like this, which is actually called a difference of squares. This is m squared minus 5 squared. And how do you figure out what two polynomials to multiply to get it? So as we make our way through these, every time we come to a product, take a look at that product and see how could you figure out what two polynomials multiply to give it. So for this next example, g squared plus 7 times g squared minus 7, I think if we were to multiply them together, we get g to the fourth minus 7g squared plus 7g squared minus 49 for a grand total of just g to the fourth minus 49. And I want us to think about, if we were given g to the fourth minus 49, could we determine what two polynomials would multiply to give this? Okay. In our next example, I think we would end up with a product of 9x squared minus 12x plus 12x minus 16 for a grand total of 9x squared minus 16. Again, all of these end up being differences of squares. Something squared minus something else squared. Something squared minus something else squared. And it's our job to figure out how can we go from this back to determining which two polynomials multiply to give it. Alright, and for our last example, if we multiply this together, we get p squared plus p times the square root of 8 minus p times the square root of 8 minus the square root of 8 times the square root of 8, which by definition is 8. Again, these two terms in the middle are going to add to 0. We end up with just p squared minus 8. Okay, so now, in general, if we are ever multiplying two polynomials of the form a plus b times a minus b, whatever a and b might be, the product is always going to end up being of the form a squared minus b squared. And this we call a difference of squares because it's 1 squared minus something else squared. And so what we're going to do in this lesson is identify polynomials that look like this and then factor them into the two polynomials that multiply to give it. So this strategy is going to work only when our polynomial has exactly two terms in it. Before, when we were factoring perfect square trinomials, well, they had to be trinomials. They had to have three terms. This strategy works when our polynomials have two terms. So let's take a look here. First things first, we always want to put our polynomial in standard form, and we want to look for common factors. So first, let's put this in standard form. That's m squared minus 9. Okay, no common factors. Let's see if this polynomial fits this form. And let's look at our first term. M squared, that is definitely a perfect square. That is the square of m. Is 9 a perfect square? Absolutely, that is 3 squared. So, do we have a polynomial of this form? Something squared minus something else squared? Absolutely. Therefore, we can determine that this polynomial can be factored as m plus 3 times m minus 3. And if you want, you can always multiply these together to confirm that this would be your product. All right, moving on. This polynomial is already in standard form. Phenomenal. Let's take a look at the two terms and see if they are perfect squares. So g squared, that's definitely a perfect square. That is the square of g. 64, that is also a perfect square. That is the square of 8. All right, it fits the form, so we can factor this as g plus 8 times g minus 8. And we have successfully factored that difference of squares. Again, we could always just multiply this out to confirm. All right, last one. B squared plus 25. All right, let's take a look at this first term. Is it a perfect square? Absolutely. It's the square of b. Let's take a look at 25. Absolutely a perfect square. That is the square of 5. However, this polynomial does not fit this form because there's addition between our terms instead of subtraction. If we were to try to factor this as b plus 5 times b minus 5, well, look what would happen if we were to multiply these two together to confirm. We would end up with b squared minus 5b plus 5b minus 25. These two add to 0. We'd end up with just, b squared minus 25. Oh, so this is not a difference of squares, and hence it does not factor like this. Now you may be thinking, maybe just b plus 5 times b plus 5 again, right? Maybe that would be the way to factor it. But be careful, b plus 5 times b plus 5, that's going to give us b squared plus 5b plus another 5b plus 25 for a grand total of b squared plus 10b plus 25. So while we did get a b squared and we did get a 25, we've got this 10b in the middle, and this is actually the factorization for a perfect square trinomial, namely this one. So we've got to be really careful when we're looking for binomials that we can factor using this strategy. We got to make sure that it is a difference of squares, not a sum of squares. All right, now it's just all about doing some examples. And I'm going to keep this up here in the corner so we can refer to it as we make our way through. All right, let's take a look at p to the 4th minus 16. It's got two terms in it, so we're thinking, okay, maybe this could be a difference of squares. Do they have, it's already in standard form, that's great. No common factors, all right, let's make moves. So p to the 4th, is that a perfect square? Yes, it is. This is what we get when we square p squared. Okay, so that's a perfect square. Is 16 a perfect square? Absolutely. That's 4 squared. So this we can factor as p squared plus 4 times p squared minus 4. Woohoo! Awesome! But check it out. We're not actually done yet. Why? Check it out. I think we have another difference of squares right here. P squared is a perfect square, and 4 is a perfect square. So we can factor this part even more because we have a difference of squares. This part we can't factor anymore because it's a sum of squares. So the full factorization in this case would actually be, we'll keep this the same, p squared plus 4. But then the second part we'll factor as p plus 2 times p minus 2. So you got to always keep that in mind with these problems that you might be able to go further. All right, moving on. Negative 5 plus a squared. First thing I want to do is put this right into standard form. So a squared minus 5. Okay, first term, is it a perfect square? Absolutely. That is a squared. Second term, is 5 a perfect square? Well, we normally really wouldn't think of 5 as a perfect square, but is it the square of something? Because if it's the square of something at all, then this polynomial will fit our form. And in fact, 5 is the square of something. What is it the square of? The square root of 5. So, this polynomial does fit this form, and we can factor it. How? As a plus the square root of 5 times a minus the square root of 5. And you can multiply this together to confirm that this is indeed what you would get. So even though 5 isn't a perfect square, as we're used to thinking about it, we can still factor it. So maybe that'll make this next one a little easier. For instance, d squared, definitely a perfect square. Is 8 a perfect square? Well, all right. Is it the square of something? Absolutely. It is the square of the square root of 8. And so we can factor this now as d plus the square root of 8 times d minus the square root of 8. Awesome, awesome, awesome. All right, making moves. Okay, so we've got a binomial here, and it's already in standard form. That's great. Any common factors? Oh, there are some common factors. Okay, I'm seeing a common factor of 2, But instead of factoring out just a 2, I'm actually going to factor out a negative 2 because I want the leading coefficient of what's left to be nice and positive. So if we factor out a negative 2 here, we're going to get a b squared, and that's the idea. Awesome. A nice positive 1 b squared minus 4. Awesome. Hopefully you can already tell this is definitely a difference of squares. B squared minus 2 squared. So we can factor this as negative 2 times b plus 2, b minus 2. And this is our complete full factorization of this polynomial here. All right, let's make more moves. First things first. All right, let's put this in a standard form. That is the same as negative 5w to the third power plus 35w. All right, common factors? Yes. I see a 5 from both of them and a w in both of them. And I'm going to actually factor out a negative 5w, so the leading coefficient of what's left will be nice and positive. So we're going to factor this as negative 5w times the quantity of w squared minus 7. All right, now let's look at what we've got left. Could this be a difference of squares? I think so. W squared, that's not so bad. That is the square of w. What about 7? Not necessarily a perfect square, but it is the square of something, namely the square root of 7. So we can factor this part as w plus the square root of 7 times w minus the square root of 7. And of course, we want to bring down that common factor of negative 5w from before. So we have our full, complete factorization right here. Awesome. Just a few more. Let's take this and kind of move it out of the way, shall we? Yeah, that's a lot better. Okay, here we go. This guy is already in standard form. Phenomenal. Are there any common factors? Nope. All right, let's see if we've got any perfect squares here. 25w to the second power, that is definitely a perfect square. That's what we get when we square 5w. What about 9? Is that a perfect square? Absolutely. That is 3 squared. So I think that this guy can be factored as 5w plus 3 times 5w minus 3. And you can always multiply this out in order to confirm that this is the product you would get. Maybe you can do it mentally, maybe you have to actually write it out, but alas, always a good idea. All right, last example. Now, this is why it's really important to find common factors right away. This guy is already in standard form, and maybe you can tell right away that this guy has some common factors. But it might be very tempting to immediately say, oh, this is a perfect square, and this is a perfect square, and call this, 4g squared plus 8 times 4g squared minus 8. But then we have all these, then we got some common factors here, we got some common factors here, there's going to be even more factoring to do. It might get a little bit sloppy and hard to keep track of everything. So really, really important for this one, start, please, 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 even though this is a difference of squares right now. This is a perfect square and this is a perfect square. Please, 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 find those common factors first, and I'll show you why. So for instance, I think we have a common factor of 16 here. So I'm going to factor out a 16, yielding 16 times g to the fourth minus 4. Okay, now let's look at our remaining binomial. Could this be a difference of squares? I think so. G to the fourth, that's what we get when we square g squared. And 4, well, that's obviously a perfect square. So we can factor this part as, let's take down that 16 because that's always a good idea. 16 times g squared plus 2 times g squared minus 2. And we're not done yet because g squared minus 2, that is another difference of squares. G squared is, well, g squared. And 2 is the square root of 2 squared. So we can factor this guy here at the end as g plus the square root of 2 times g minus the square root of 2. And of course, we're going to carry down all the other stuff we had. 2 plus g squared and the 16. And so this right here at the end, this is our complete final factorization of this original polynomial. So just goes to show, always a good idea, of course, put it in a standard form and look for that common factor first. So That's it for this lesson. I hope you guys liked it, and I hope you found it helpful.